Hi everyone, welcome to this video where we'll dive into the implementation of basic diffusion models using TensorFlow and Keras frameworks. Diffusion models have become a cornerstone of modern visual generative AI, powering tools like Dall-E, Imagen, Midjourney, Stable Diffusion, and many others. Historically, high-quality image generation has been largely driven by the generative adversarial networks, or GAN in short. While GAN has been a great success, they seem to be reaching the limit at the moment, where the training process remains unstable and tend to run into the condition that we call it as the mode collapse. That is, they only capture a small part of the true data distribution. On the other hand, diffusion models have successfully provided both stability and high coverage of data distribution while maintaining the high quality image generation at the same level or even better than GAN. In this video, I'll walk you through the code implementation that explains the basic intuition behind diffusion models, how forward diffusion and reverse diffusion process work, the inference and sampling techniques, the training algorithm of diffusion models, and last but not least is the model architectures, which is the unit architectures as the backbone of diffusion models. Let's jump right in. At its core, a diffusion model is inspired by the natural process of diffusion in particle physics, where particles spread out from areas of high concentration to the low concentration. Think of it like pouring a drop of ink into water. Initially, the ink is concentrated in a tiny area forming a distinct shape, and as the time goes by, the ink particles begin to spread throughout the water, gradually blending into the liquid until the color is evenly distributed. At this point, the original structure of the ink drop is gone, and all that remains is sort of a homogeneous mixture. Diffusion models in AI mimic this process, but in reverse. Instead of starting with structured data and destroying it, these models begin with random noise and learn to transform it back into the meaningful data, such as text, images, or video. The basic idea is to train a neural network to reverse this diffusion process step by step, reconstructing the original data from the noise. Now, let me show you the diffusion and its reverse process for image generation in more details. I'm just going to open the now highly cited paper called Denoising Diffusion Probabilistic Models, written by the fellows from the UC Berkeley, where they show empirically that diffusion models are capable of generating high-quality samples, similar or even better quality than several state-of-the-art generative models at that time. In general, diffusion models are probabilistic latent variable models, where the dimensionality of the latent variables is the same as the input dimension. The forward diffusion process is modeled probabilistically by the conditional distribution Q of xt given xt minus 1, taking a Markov chain trajectory from the right to the left here, dispersing the original image x0 up to the state of the pure noise x capital T. The conditional distribution Q of xt given xt minus 1 here actually has a closed form solution, which can be computed analytically, something like this. Meanwhile, the reverse diffusion is also modeled by a conditional distribution. In ideal world, the reverse conditional distribution Q, meaning Q of xt minus 1 given xt, could play the role as the Markov chain model for the reverse diffusion from the left to the right trajectory. However, computing Q of xt minus 1 given xt by taking the base rule from Q of xt given xt minus 1 is intractable, since it needs to consider all samples when computing the marginal distribution. So the reverse diffusion process is approximated with a parametric model p theta of xt minus 1 given xt, where the parameters consist of neural networks. Let's scrutinize this diffusion process one by one. For the forward diffusion, the conditional distribution Q of xt given xt minus 1 follows a multivariate Gaussian distribution, where the mean is the weighted values of the previous samples xt minus 1 with the square root of 1 minus beta t as the weight. And the covariance is the weighted identity matrix with beta t as the weight. So it tells us how much noise we're going to give to destroy the original image at a certain time step t, step by step, where the coefficients between the mean and variance are related to each other. If we break down the equation for this conditional distribution Q, it's actually forming a linear combination between the previous samples xt minus 1 and the Gaussian noise epsilon with zero mean and unit variance. Here, the weight becomes alpha t, which is just a substitute from 1 minus beta t, as shown in this excellent blog post by Lilian Wang. So the forward sampling strategy is basically computing this first equation. Note that using this raw equation to perform sampling computation is going to be time consuming, since we need to always compute the sequential process starting from 0 just to get to a specific state of time step t. To simplify the computation, this equation has a nice property that it can skip all the intermediate sampling steps by this algebraic manipulation, where we end up with the linear combination between the original sample x0 and the fixed Gaussian noise epsilon. So we don't need to compute all the intermediate samples of, for example, x1, x2 until xt minus 1 to get the final state xt. I'm going to show you a picture taken from another excellent article um, that hopefully can give you a better understanding of the difference between the raw sampling equation and the simplified one. So we only control the amount of the coefficient alpha bar t here to get the clutter samples at time t, rather than running through the step-by-step calculation from the original sampling strategy. Now let's take a look at the code implementation. Here I already prepared a Python function implemented with Keras and TensorFlow called forward diffusion, taking the original input image x0, the initial noise, and the number of steps as inputs. The most important part of this function is this following block code. Particularly this line showing the noisy images equals signal rates times x0 underscore n plus noise rates times noises, which is basically implementing the simplified sampling equation. So the alpha bar t here are represented with signal rates, and the square root of 1 minus alpha t are represented with noise rates. And those coefficients are computed through a particular diffusion schedule strategy. And in this implementation, I actually run the cosine stepwise scheduling rather than using the linear stepwise as described in the original DDIM paper. So let's run the simulation here. I'm using images from the Cypher 10 dataset. And here I just take one single image and define the number of forward sampling steps equals to 5, and calling the forward diffusion function as I explained before. Let's run it. It might take a while. Here we go. So it's simulating the forward diffusion with 5 steps, taking the original image from the Cypher 10 dataset. And we can see the image is getting destroyed with this forward diffusion scheduling by considering the level of noise rates and also the signal rates until the step number 5. For the reverse diffusion, it is modeled with another conditional distribution, which is p theta of xt minus 1 given xt, which again takes a form of Gaussian distribution, but now with mean and variance inferred from the neural networks. This is where the neural networks will do the magic in generating high quality new samples from the noise after being trained properly, obviously. Let's go to the source code again. Here I have the reverse diffusion function taking the initial pure noise and the number of steps as inputs. And this function is performing the denoising process of the noisy samples in the hope that it's getting closer to the clean version of them over time. Firstly, I'm using the same diffusion scheduling as the forward division to set the signal and the noise coefficients, which is the continuous cosine stepwise sequence, but now in reverse direction from the last state to the origin state. And here is the core of this module, in which neural networks are run to predict both the noise delta and the cleaner image, given the noisy image from the previous step, controlled by the signal and noise coefficient derived from the diffusion scheduling. It is also important to note that the neural network performs the denoising indirectly, in the sense that it first compute the noise delta, and then we do the post-processing to get the cleaner sample. Let's zoom a bit into the denoise function here. So here we can see that there is a neural network represented by the Keras model that receives noisy image and noise rate as inputs and predict the noise delta. And then we're going to use the noise delta to shift the noise image into the direction to get the cleaner version of it, and then normalize it with the signal rates. The reason we are doing this is it's much easier to capture the noise delta structure than the actual structure of the image, and it happens to provide higher quality samples, as is empirically shown in many papers. I also want to highlight that the reverse diffusion function here is implementing the sampling mechanism from another paper called Denoising Diffusion Implicit Models, DDIM. DDIM sampling is able to provide much faster sample generation by simply removing the Markov chain assumption. This means that we're not going to use the randomness from the variance of the Gaussian distribution, so it becomes a deterministic process rather than the stochastic process. By doing so, it's enough for DDIM to get high quality samples as good as DDPM with much fewer sampling steps. Let us run the code to simulate the reverse diffusion. So I'm gonna disable the forward diffusion computation and activate the reverse diffusion. And let's assign the reverse step into, let's say, 10, and define the initial noise by the normal distribution, and then run the reverse diffusion calculation. Let's see. Okay, now we able to simulate the reverse diffusion process by taking a random pure noise and then gradually declutter the noise into a cleaner version of the image until steps number 10. Now we're going to explore the training algorithm of the diffusion models. While the mathematics behind the algorithm is quite complex, especially if you're not familiar with the variational inference, the practical implementation is pretty simple. The basic idea is to guide the output of the neural networks through the reverse diffusion process to be as close as possible to the samples generated by the forward diffusion, including the original sample. This can be achieved through the gradient-based optimization or standard backpropagation. Let's go back to the DDPM paper, where we can see the pseudocode of the algorithm. So it's an iterative process where first we take a sample from the training set, And then we pick a time step according to this uniform random distribution, and also specify the random noise epsilon based on this Gaussian distribution. And finally, we run the backpropagation guided by this gradient with respect to the following loss function until the convergence. If we see these least square functions more carefully, it actually resembles the denoising score matching, meaning we compare the expected noise with the predicted noise as the result of the forward and reverse diffusion rather than taking the actual samples directly. As we've discussed before, this denoising score matching approach happens to produce better results than the original formulation. Let me go to the code again. Using the Keras framework, we can implement this training procedure inside the extended class Keras model, which I name it as DDIM here. Particularly, the algorithm is implemented under the function called train underscore step. This is actually almost one-to-one translation from the pseudocode that we've seen before. The only difference is it takes the input samples already in a batch mode. So after getting the samples randomly from the training set, we take the diffusion time steps according to this random distribution to calculate the noise and signal rates. We then use those noise and signal rates to calculate the one-step forward diffusion to get the noisy images. We also compute the one-step reverse diffusion given the noisy images from the forward diffusion to get the predicted noise and also the predicted images. And then we calculate the loss function, taking the expected noise and the predicted noise as inputs, which is basically the denoising score matching here. Of course, we need to calculate the gradients and also update the uh, network parameters driven by the gradients before. Finally, this is the step that actually not part of the main diffusion algorithm, but it's important for the entire training and the inference process of the diffusion models. This is the regularization called the exponential moving average, EMA, which is actually already widely used techniques to regularize the neural networks, especially to maintain the stability and hopefully produce better generalization of the model. So the core idea is to let the weight updating to get influenced by the previous values of the weights as well, not only relying on the recent gradient information, so that the weight updating is not going to be too fast and introduce more stability over time. So here I already run the main training script called the training.py here, which actually taking the Cypher 10 image as the samples. And here, because we already implemented the algorithm inside the train step function in Keras model, we can simply call the general fit function to start and execute the entire training process. And here I use the number of iteration of epoch to be equals to 50 epochs. So let's also check the generation results of this training process, since I also make some checkpoints of the reverse diffusion output. And here, this is the reverse diffusion result of the first training iteration. So we can see that over time, it's starting to generate some sensible images mimicking the actual image input. At the heart of most diffusion models is the UNet architectures. UNet is a convolution network, as displayed here, which excels in capturing both local and global information. It features an encoder-decoder structure with skip connection or shortcuts, connecting a particular encoder layer to its corresponding decoder layer. This allows it to retain fine-grained structures of the image while processing high-level abstractions. In the context of diffusion models, the encoder extracts features from noisy inputs, and then the decoder uses these features to reconstruct the data. Skip connections ensure no critical information is lost during the process. Here, I implement the unit architectures inside the architectures.py script here within the create unit function, receiving image dimension, channel, widths, and block depth. In the input layer, we see that the network has two types of inputs as the placeholders for the image input and also the noise rates. It's important to explicitly capture the noise rate in the diffusion model to let the model knows at which stage it's gonna run the reverse diffusion process. Next, we compute the sort of embeddings for each type of inputs. It's pretty straightforward for the image input, which just applies the 2D convolution layer. For the noise rates, we apply the sign embedding function through this Keras lambda layer, which is basically converting the original scalar values into their unique vector representation, and then followed by the 2D upsampling layer so that we can concatenate the image embeddings with the noise rate embeddings because they are both in the same dimension now. After that, we define the encoder structure containing several downsampling layers. Inside these downsampling blocks, it is basically containing several residual blocks followed by the average pooling layer with the number of dimension keeps decreasing until the middle or bottleneck blocks here. And then the network structures ends with the decoder structure, which consists of several upsampling blocks, which is basically similar to the downsampling blocks, but with the number of layers keeps increasing up to the output layers. Finally, the stack of all those layers is encapsulated with the Keras model class. Note that the use of the unit architectures in the diffusion models is necessary but not mandatory. We can use any other model architectures, for example, transformers, similar to the architectures of the large language models, which are also used recently in many powerful visual generative models. We can have a quick check of the unit architectures by running this create unit function. Let's see. So we can see that the model summary visualization here shows the decreasing dimension of the encoder structure of the unit, and then showing the decoder structures with this increasing dimension of the layers. So that's all about the basic diffusion models, including their core processes and how they're implemented with TensorFlow and Keras. I hope this gave you a clear understanding of how these powerful models work and how they're shaping the recent trend of vision generative AI. Of course, what I've shown here is still not enough to build more powerful generative models. To enable the image generation, for example, through the natural language prompting, like Stable Diffusion, Imagen, or Sora, we need to integrate it with large language models, making sure that the text embeddings in LLMs are linked to the image embeddings in the diffusion models. Furthermore, we need to enlarge the size of training samples and also the network architectures. If you're curious about the code, check out the GitHub repository in the description below. Thank you for watching, and I'll see you in the next video.